Hello, welcome to our short video on how to design a single supply, second order, multiple feedback, high-pass filter circuit. This schematic represents a single supply, second order, multiple feedback, high-pass filter circuit. Multiple feedback filters are preferable when the gain is high or the Q factor is large, for example 3 or greater. This high-pass filter circuit has a gain of -1 volt per volt, which simply inverts the signal in the passband. It utilizes a single 5-volt supply and a 2.5-volt reference voltage. The first step in this design is to calculate the component values given a normalized cutoff frequency of 1 radian per second. The second step is to scale the component values for 1 radian per second using the desired cutoff frequency. This slide depicts the design goals and transfer function of the circuit. The input signal ranges from -2.45 volts to +2.45 volts, and the output swing is from 50 millivolts to 4.95 volts. As mentioned earlier, the design uses a single 5-volt supply, a 2.5-volt reference, and has a gain of -1 volt per volt. The desired cutoff frequency is 1 kHz, and maximum frequency is 10 kHz. The transfer function, h of s, and equations for A1 and A0 are given to the right of the schematic. While these equations look complicated, the methodology presented here greatly simplifies the design process. In the first line, we set the normalized cutoff frequency, omega c, to 1 radian per second. Look up the values of A0 and A1 in TI's active low-pass filter design application report and set the normalized values of C1, C2, and C3 to 1 farad. Please note that the subscript n is used to represent the normalized values. These values will be adjusted later. The second and third lines calculate the normalized values for R1 and R2, which will also be adjusted later. Now we need to scale the cutoff frequency and the component values. M is known as our scaling factor. If we scale R1n and R2n by a factor of m, we will then have to scale C1n, C2n, and C3n by 1 divided by m. Also, we have to scale the cutoff frequency from omega c to omega naught. Therefore, you'll notice that the capacitor values are scaled by 1 divided by omega naught. Now let's calculate our scaling factor, m, and resistors R1 and R2. For this filter, we're going to select the capacitor values first. In this case, let's pick a standard value of 1 nanofarad for C1, C2, and C3. Given the cutoff frequency design goal of 1 kHz, we can use the equation to calculate our scaling factor, m. The value of m is 159,155. Now we can use the scaling factor, m, to calculate R1, which is equal to 75 kiloohms, and R2, which is equal to 336 kiloohms. The final step is to ensure that the selected device, TLV9062, has sufficient bandwidth and slew rate to meet the maximum frequency requirement of 10 kHz. It is important to use the noise gain for this calculation. The noise gain for this circuit is 2 volts per volt. Do not use the signal gain of -1 volt per volt. As a general rule of thumb, we multiply the minimum bandwidth required by 100 to account for any variations including process and temperature. This yields a desired op-amp bandwidth of 2 MHz. Depending on your design needs and environment, you can adjust this rule of thumb as needed. However, one of the most common mistakes in designing filters is insufficient bandwidth. The minimum slew rate for this circuit is calculated to be 0.154 volts per microsecond. The TLV9062 has 10 MHz of bandwidth and a slew rate of 6.5 volts per microsecond. Therefore, it easily meets the minimum requirements for this circuit. Running an AC sweep analysis, we find the cutoff frequency of 1 kHz as desired. Also, the design meets the maximum frequency of 10 kHz. Running a transient analysis at 10 kHz shows that the input signal passes without attenuation to the output. Note that the output is centered around our reference voltage of 2.5 volts. Running a transient analysis at 100 Hz shows that the input signal is attenuated. The output is a near DC result of 2.5 volts. When designing active filter circuits, there are a few design notes to be aware of. First, select an op-amp with sufficient common mode and output swing range, and add a reference to bias the amplifier in single supply designs. Next, use high precision, low drift passives to minimize errors. Finally, be sure to select an op-amp with sufficient bandwidth and slew rate. Texas Instruments has many online resources to help you design circuits with op-amps. This includes reference designs and guides, educational videos, simulation and prototyping tools, support resources, and search tools. Thank you for taking the time to watch this short presentation on how to design a single supply, second order, multiple feedback, high-pass filter circuit. Please visit www.ti.com for additional information and resources.